Imagine trying to change the engine of an airplane mid-flight with a billion passengers on board. That's pretty much the scale of the challenge Facebook's engineers faced when they decided to swap out the core database technology for their entire social graph. So, how in the world did they pull it off? Let's get into this incredible engineering story.
First, to really get the stakes here, we have to talk about scale. We're talking about Facebook's user database, the UDB, which manages tens of petabytes of data. I mean, that's millions and millions of gigabytes. It's the digital lifeblood of our likes, our comments, our shares, all our connections. And this absolute behemoth of a system was heading for a crisis.
And this wasn't just some, what-if scenario for Facebook. This was a real ticking clock. Their existing database was seriously struggling, it was eating up way too much space and putting a ton of wear and tear on the super expensive hardware it was running on. They needed a totally radical solution, and they needed it yesterday.
So, what was the root of the problem? Well, it wasn't that Facebook's original database engine was bad or broken. Not at all. The problem was that the ground had shifted underneath it. The hardware it was built for had completely changed, and that change turned the engine's greatest strengths into some of its biggest weaknesses.
See, the whole industry moved from these slow-spinning hard drives to unbelievably fast flash storage, or SSDs. That fixed the speed problem for sure, but it created two new massive headaches. One, Flash was really expensive, so every single gigabyte of wasted space cost a fortune. And two, Flash has a limited lifespan. It literally wears out the more you write data to it. All of a sudden, the name of the game wasn't just speed anymore, it was about squeezing every bit of space and being as efficient as possible with every.
And this is exactly where their old engine, called InnoDB, was really starting to hurt. First, it was wasting up to 30% of its space just from fragmentation. Think of it like a bookshelf with these huge, awkward, unusable gaps between all the books. Second, its compression just wasn't very efficient. If it squished a chunk of data down to 5 kilobytes, it still had to use an 8 kilobyte parking spot on the disk. And the real killer was this thing called write amplification. To change just one word in a book, it had to rewrite the entire page, and a backup copy of that page. This was just burning through their expensive flash storage like crazy.
Okay, so with all these problems piling up, it was super clear they needed a new engine, one that was actually designed for flash storage from the ground up. But they couldn't just rewrite every single application that talks to the database. I mean, that would be totally impossible. So instead, they found a much more elegant solution. This is where they got really smart. They kept the top part of their database system, MySQL, the part that all their apps already knew how to speak to, and they used its pluggable design to just swap out the storage engine underneath. It's kind of like keeping the body and dashboard of your car, but dropping in a brand new high-efficiency engine. They chose an engine based on a technology called RocksDB, and their creation was named MyRocks.
So what's the big difference here? Well, the old engine, InnoDB, used what's called a B tree. The best way to think about that is like a perfectly organized library. It's super fast to find a specific book, but adding a new one and having to reshuffle all the shelves to make it fit, that's really slow and complicated. The new engine, MyRocks, uses something totally different called an LSM tree, and that's way more like a journal. Adding a new entry is incredibly fast. You just write it at the end. To find something, you just check the newest entries first, then look in the organized back catalog. For a system like Facebook where new stuff is being written all the time, this was just a perfect fit.
And this diagram gives you a peek at how that journal actually works under the hood. New data gets jotted down really fast into a temporary spot in memory. Then it's quickly saved into these small files. And over time, this background process, like a helpful librarian, comes along and neatly merges and organizes these small files into bigger, more permanent ones. This whole layered approach is the secret sauce to its amazing write speed and space efficiency.
But, nothing's ever that easy, right? MyRocks wasn't some magic wand they could just wave. This new LSM tree design brought its own set of really unique and tricky problems that required some seriously clever engineering to fix before it could ever handle Facebook's scale.
So, the first huge problem was basically a graveyard of deleted data. In an LSM tree, when you delete something, you don't actually erase it. You just add a little marker next to it, a tombstone, that says, hey, this is deleted, just ignore it. But the problem was, these tombstones would just hang around forever, clogging up the database and making queries dramatically slower.
So what was their fix? Well, it was brilliant. They basically invented a new, smarter kind of tombstone they called single delete. You can think of it like disappearing ink. As soon as this special marker finds the exact piece of data it's supposed to erase, poof, it vanishes, cleaning itself up almost right away instead of just lingering for ages and slowing everything down. All right, next problem, speed. Because the LSM-trees data was scattered across all these different journal files and levels, certain types of searches, like trying to fetch all the comments on a single post, were way too slow. The database was wasting a ton of time looking for data in dozens of different files where it didn't even exist. Their solution was a really cool optimization called a Prefix Bloom filter. The easiest way to picture it is like a hyper-efficient bouncer at the door of each data file. Before trying to go inside, the database asks the bouncer, "Hey, do you have any comments for this specific post?" And the Bloom filter can instantly say, "Nope, don't even bother looking in here." By telling the database where not to look, it saved thousands of useless searches and made these crucial queries fast enough for the real world. All right, so they've tamed the new engine, they've solved the big problems. Now for the scariest part of all, performing the actual migration on the live database for billions of users without anyone even noticing. No pressure, right?
To pull this off without, breaking Facebook for everyone, they built this incredible tool called MyShadow. It was literally a flight simulator for their database. It would record real live traffic from the production system and then replay it perfectly against test copies that were running the new MyRocks engine. This let them find all sorts of bugs and performance issues in a completely safe environment before a single user was ever impacted.
And the migration itself, well, it wasn't like flipping one giant switch. No way. It was this incredibly careful, meticulous, multi-stage process. First, they added the new MyRocks servers as read-only copies, just to watch them. Then, once they were totally confident, they promoted one of the MyRocks servers to be the new primary that handled all the new data. And only after months of proven stability did they finally start taking the old InnoDB servers offline. It was just a masterclass on how to manage risk at scale.
So after all that work, years of development, all that testing, and that super stressful migration, was it worth it? Did all this effort actually pay off in the end? Oh yeah, it was worth it. Their main goal was to slash the database size by 50%. They didn't just meet that goal, they totally blew past it, achieving a massive 62.3% reduction in space. When you're talking about petabytes, that is just an astronomical amount of savings. And remember that whole problem with the flash storage wearing out? Well, get this. MyRocks cut down the amount of data being written to the disk by a mind-blowing 75%. This meant their super expensive hardware would last significantly longer, saving them even more money and resources down the line. And this table really just puts it all in perspective. You can see the absolutely dramatic drop in space usage and the bytes written. But here's the kicker. Look at the CPU columns. Despite being massively more efficient on storage, MyRocks was also slightly more efficient on CPU. I mean, that's just a win across the board. And here it is, the real bottom line. What does all this efficiency translate to? It meant Facebook could run its entire social graph on less than half the number of servers they needed before. That is a staggering, game-changing improvement in efficiency. The success here was so profound that it created this ripple effect across the whole company. It gave them the confidence and the green light to go after another massive database system, the one powering Facebook Messenger. They used the exact same MyRocks technology to move it off its old system, proving the value of this approach across the entire company. You know, this whole incredible story really boils down to one thing, a fundamental trade-off, all driven by a change in hardware. They sacrificed a little bit of read-lookup simplicity to gain this massive advantage in space and write efficiency. And it really makes you wonder, right? As our world generates more and more data and new technologies keep emerging, what's going to be the next great trade-off that powers the internet of the future?